Hello, this exercise 21B.2. We looked last time at how to find the coefficient of friction, and we found that we have this formula F. As long as it's moving, F equals mu R, where R is the normal contact force pointing upwards from, and very often determined by the weight of the object too. And friction here. This is meant to be, I think, the tension. Usually we're written with a capital T, but this one, for some reason, someone's put a small t. And I suppose that's all very well and good, and this F equals mu R is a very, very important equation to use, assuming that we've overcome the minimum amount required to make it move. Then this is what we get. And what we're doing today is looking at that again, but also notice we've got this C. And this C is what we'd call the resultant contact force. So it's a force which is effectively the result of having one force here, which is a contact force, which is called the friction, another force here, which we call the normal contact force, the force that goes straight up. And effectively, they're both acting on the object, so if you combine the two together, you get this contact force, the overall resultant contact force. So I want to do that, but I've got a couple of starters to look at first of all. A force of magnitude 2, there it is, 2, is at an angle of 50 degrees to the horizontal, and we've got a 300 gram, so this is the weight of this, if it's 300 gram, is 0.3. Don't forget it's mg, so we times by 9.8. I think that's 2.94 Newton. So after a while you get to learn these. So we've got the weight. Don't be fooled, by the way. This is going to be, will need to be resolved. I know it goes up there, but we are going to work on sort of horizontally and vertically. And so horizontally, this becomes 2 cos 50. And you should know how to resolve it. And I'm going to draw two forces going up. One of them is the fact that it's 2 sine 50, because it's not only pulling left, it's pulling up as well. But also we've got the normal contact force. We always get a normal contact force whenever something is acting. And presumably there's a friction as well. Look at this. All these forces have appeared suddenly. The 2 really is the main force. And I've replaced it with these two components of that force. So anyway, so what are we doing? It's on a rough table, which I assumed. What's the range of values for the coefficient of friction? Well, first of all, I suppose I want to find R. R plus that 2 sine 50. They're the forces going up, you see. If I've resolved this 2, it's 2 sine 50 plus the R, and that's got to equal the W. So I know it's 2.94. So if I do 2 sine 50, make sure I'm in degrees. I am now. So 2 times sine 50, and I've got to do 2.94 minus that. When I move it over, it will obviously become a negative, and I get 1.41. So I now know what R is. It's 1.41 newtons. And I suppose I can do something similar going left and right, because you see this stays at rest. So basically, these two things, F has got to equal 2 cos 50. So what is 2 cos 50? 2 times cos 50 is 1. Well, it's 1. I'm going to be a bit more accurate on this, by the way. 1.408. Give myself one extra decimal place, and this is 1.286. That's what this friction is. Now, bear in mind though, F is less than or equal to mu R. That's our formula. Now it could be normally, if it was actually moving, I'd say it was equal to mu R, but it's not moving, so therefore it could be that we haven't quite got up to the maximum amount of friction yet. So the friction is less than or equal to mu R, so I can write here my friction, which I've calculated. All it's needed to do at the moment is at rest. The force applied to it is this 1.286. So it's 1.286 the other way. But that's got to be less than mu times by my R. What was that? 1.408. So I just think my mu, if I move that around, is greater than or equal to 1.286 divided by 1.408. What is that? Divided by 1.40. a little bit more. 0.913. So I reckon mu is greater than or equal to 0.913. Good. A particle of mass 2.3 kilograms rests on a rough horizontal surface. Okay, so I'm just reading this here. There's a couple of things I want to say. M is 2.3. We can write that straight away. And we also get told that the coefficient of friction is 0.25. Okay. The unit vectors I and j are in a horizontal plane. So I think this is us looking down on it. So I want you to imagine our particle here. There's the I direction. And there's the j direction. And two horizontal forces are acting on this particle. 3j, oh, a bit naughty straight away. Look, I'm going to write F1. I don't like that. F1 is, look at this, the i's and j's are all the way around. Minus 2, 3. And F2 is 6i, so that's 6, 0. So what does that actually represent? Well, we've got a force going this way. That's my F2. That's my 6 across and 0 up. And I've got this force 2 left, 3 up. There, something like that. Now, it's not drawn to scale, clearly. But these two forces acting. And between them, does it say the unit vectors, two act on it? The frictional force is this. And I'm assuming here, well, what I want to do, I suppose, I need to find out, and this is something which is slightly different to what we would have perhaps have done in the past. I need to say to myself, what is that overall force that I'm giving it? So I'm just going to do it down here. F1 plus F2. Using what I've done there, I reckon that's 4, 3. And I think I need to know the magnitude of this force. So the resultant force, which I've called F, that's a bit dodgy actually, I'll call it RF instead so I can tell the difference. So the resultant force is 4, 3, and therefore I can find its magnitude by doing Pythagoras, 4 squared plus 3 squared, which is 25, and you do it, square root is 5. So I now know the resultant force applied to this object is 5 newtons. And because it's slightly left and slightly right and slightly up as well, I think it's probably, well, I can tell you where it's going, it's 4, 3. So it's actually doing that. That's the resultant force. It's going in that direction. So the question is that enough to make it move? Well, I can do that by just doing F equals mu r. Now I know my magnitude of my force and not just the vector. The vector can be a bit deceiving. But what's my magnitude of the frictional force? What's the maximum I can get up to? Well, I know that F max is mu r. Or F is less than or equal to mu r if you prefer. So F max is mu r. Now what was that? It was 0.25 times r. Now let's think about what r is, because I don't think we quite cleared it up. I mean, this is, remember, the plan view. The plan view is what you see when you look down on it. Whereas I think what we've got now to think about is, what if you looked at it from the side? The side view would show, here's my ball sitting on the floor, it's got a weight, and it's got a normal reaction. And of course, it's that normal reaction that I need to find here, this normal contact force. So what was the weight? It was 2.3 times by 9.8. So what is 2.3 times 9.8? 22.54. That's definitely not one you know off the top of your head. And of course, weight equals this r, because there's no other forces acting up and down. So this is also 22.54. This is 22.54. So if I can find my max times by 0.25, and I get 5.635. So the maximum we can get up to in terms of friction is 5.635 newtons. What's my result? My resultant force was only 5 newtons. So I can tell you now it's not going to move. And since it's not going to move, our friction force will only just equal what we got given, effectively, and it will be equal and opposite, or act in the opposite direction. So I earlier on said my resultant force was here. It was going 4 across, 3 up, according to my formula here. It was 4 across, 3 up. So I reckon this has got to go the opposite way. This is where my friction goes that way. Friction equals -4, -3. There you go. A third force of -13 newtons is applied. Find the new frictional force. Right, so this is basically saying we've now got a third force. I think the answer is going to come up there. So I'm just going to do F1 plus F2 plus F3 now. And I'm going to say this is the resultant force, the new resultant force for part B. And of course what that equals is what we had before plus, well, what force is it? It's minus 13I. So technically I suppose it's that 4,3 that we had from our first two vectors, plus this minus 13, 0, which is this third force. And I reckon that's minus 9 and 3. And I can do a similar thing. I can find its magnitude. The resultant force is now equal to the square root of 9 squared plus 3 squared, which I reckon is root 90. And what's root 90? It's about 10ish. A bit lower, obviously. As a decimal, I'll get 9.49. So it's 9.49 newtons. Now, look, this is more than 5 newtons. Oh, 5.635 newtons, sorry. So it will move. Will accelerate, I suppose is the posh word to say that. There is a resultant force, even after the friction. So I suppose the way to do this is to say, well, how much more than it is it? See, if we knew in just one dimension, we'd just take it away. But how much more than the 5.635 newtons is it? And obviously, we just got to adjust our forces accordingly. So we have to broadly do the same as we did before. Last time, if you remember, what we did was once we realized that it didn't move, we kind of looked at this force and turned it round and said the friction force must be acting opposite it. And it's the same here. The new frictional force is going to be kind of doing the opposite of this, but only up to the limit of 5.635. So the way I do that is I do the 5.635, which is the maximum I can do, and I have to divide it by how much of a force I'm imparting on it, which is the 9.49. And then I can times it by the opposite of this minus 9.3. Remember I did that last time. It was 4.3, but I did the opposite force, in the opposite direction, if you like. So I'm going to do 9 and minus 3. So if I just do that, it's 5.635 times by that 9, and then divided by 9.49. So that's just the top one. So I get 5.34, and it's a positive, I think, that one. And then the bottom one, if you do the same thing, you should get minus, I get minus 1.78 when I typed it in, newtons. So that, I think that last one's quite tough, I'll be honest. I wouldn't be surprised if you need to look at that about 5 times. Let's see what the answers are. I just looked in the book, actually. That can't really read it. Yeah, I think this is, oh no, that's right, that's what I got. In the textbook, it gave a different answer. So interestingly, that is given the same answer. So look, we haven't got long. I'm just going to quickly mention then that we've moved towards finding these contact forces. And in the lesson, I think we need to do it properly. When you get at something moving and it's in contact, then a bit like I was showing you before. So we got this force, we got this reaction force as well, and effectively what you have is two forces acting. You have the contact force from the friction going left in this picture, and then you can imagine this coming up, the reaction force you can imagine coming up there. And if you do a bit of Pythagoras of those two forces, you can find C, the contact force, from the rough surface. So here, for instance, on this picture, I've got a weight of 25, so I've got a reaction force of 25. I'm pulling it, it's on the point of slipping. That's important because that means its friction is also 15. So notice I'm going to quickly just do this. I'm going to imagine this as 15 there, the 25 coming up here. If I do a bit of Pythagoras on that, I'll get the contact force. So quickly doing that, I did 25 squared plus 15 squared, c squared is 850, square root that, and I get 29.2 newtons for that contact force. It only wants the magnitude of it, so that's it. And in the lesson we'll do a bit more on this, but then we'll do exercise 21B.